When a reservoir hits capacity, millions of gallons of water have to go somewhere. Releasing that volume creates one of the most violent displays of kinetic energy on Earth. Engineers cannot allow a flood to spill freely over the top of a dam. The sheer, unchecked force of that falling water would tear the foundation apart, so the excess flow must be redirected through a specialized structure. But pouring that water down a simple concrete ramp is dangerous. If the fluid moves too fast over a poorly shaped edge, the flow separates from the surface. This creates areas of negative pressure that literally tears the concrete apart, a destructive process known as cavitation. Managing this chaotic force without destroying the structure itself is the ultimate test of hydraulic engineering. The solution is the spillway, specifically a highly calculated, gracefully sweeping ramp known as the OG spillway. This mathematical curve forces the fast-moving water to maintain tight surface contact, eliminating the gap and removing the threat of cavitation. The adjacent siphon spillway uses trapped air to create a vacuum, automatically sucking excess water out at a critical depth. To build these massive shapes, engineers had to reverse engineer the fundamental behavior of individual water particles. Water in motion is an absolute mess. It is composed of billions of particles, all moving at different velocities and accelerations simultaneously. This passage describes the Lagrangian method, selecting a single fluid particle and tracking its journey. For massive dams, following individual drops is impractical. Instead, engineers use the Eulerian method, picking one fixed point to observe changes in velocity and pressure as water rushes past. This 3D graph illustrates the shift. By mapping the flow to an exact set of coordinates, x, y, and z, engineers can track exactly what the fluid is doing at a stationary point in space and time. By fixing their perspective, they turn the unpredictable chaos of the river into reliable, readable data. To build a structure that will last a century, the data at that Eulerian point must be predictable. Look at these partial derivatives for steady flow. They equal 0. Proving pressure and velocity don't fluctuate over time at a specific point. Then there's uniform flow, where velocity remains constant from one point to the next along the entire channel. In reality, geography often forces a change. As these diagrams show, when a channel narrows or expands, the water must speed up or slow down to fit the new shape. The flow becomes non-uniform. Recognizing these exact states of flow is the prerequisite to controlling the incredible forces inside a dam. These observations are governed by one unbreakable rule, the continuity equation. This stream tube diagram lays out the core relationship. The area of the first cross-section, multiplied by its velocity, will always equal the area of the second cross-section, multiplied by its own velocity. Since water is practically incompressible, the math demands a trade-off. If you decrease the cross-sectional area of a channel, the velocity must increase to balance the equation and move the same volume of fluid. Engineers use this equation to determine how wide a spillway must be to ensure the water speed stays below the threshold of destroying the concrete. Early engineers tried to control high-velocity flow using simple concrete blocks called weirs, but the water quickly exposed a fatal vulnerability. This diagram shows a standard broad-crested weir. Notice the sharp 90-degree upstream edge. As the text shows, high-speed water overshoots that corner, separating from the concrete to create a dangerous air pocket. This allows cavitation to begin eroding the weir. To fix this, builders contoured the concrete to perfectly trace the natural aerodynamic underside of a falling jet of water. Returning to the OG spillway, we can see that its iconic curve is the physical solution to that air pocket. The concrete meets the water perfectly, maintaining contact and stability. The sweeping shape of a modern spillway is simply the physical manifestation of balancing friction, velocity, and pressure. Taming a flood requires a depth of engineering that reaches beyond brute force or building a wall thick enough to hold the river back. It requires applying the continuity equation and the Eulerian method to dictate exactly where the water wants to go. Behind every massive release of water lies a hidden foundation of fluid kinematics, preventing the structure from tearing itself apart. The next time you see millions of gallons of water cascading into a valley, you are witnessing a perfectly executed mathematical equation. When a severe storm stalls over a river basin, the reservoir behind a dam swells. We're looking at billions of liters of water, an unfathomable mass, pressing relentlessly against a concrete wall. If that water simply pours over the crest, a scenario engineers call overtopping, the results are catastrophic. Entire downstream communities face immediate inundation. Engineers have to balance two opposing requirements. The structure must block the river's flow, yet it also needs to discharge that same water at a moment's notice. Without a carefully calibrated pressure relief valve, a static concrete barrier cannot survive the rising force of nature. Curious, letting that volume of water simply free fall off a flat ledge isn't a viable option. Millions of liters of water dropping straight down generate an immense amount of kinetic energy. When that concentrated force strikes the riverbed, it rapidly erodes the bedrock foundation holding the dam in place. The crashing water also sends chaotic, intense vibrations echoing back up into the structure. Over time, those shock waves can shatter rigid concrete from the ground up. To survive, a dam requires a release structure that mimics a natural fluid trajectory, rather than fighting against it. The ultimate solution is the OG Spillway. It's defined by a signature sloping S-curve sweeping down the face of the dam. This diagram shows the OG Spillway cross-section, mathematically mapped to the exact trajectory of falling water. The governing equation, Q equals CLH to the 3/2 power, means as the water level rises, discharge increases exponentially. Because of this geometry, the spillway instantly self-regulates extreme storm surges, and it does so without the need for complex moving parts. If the concave curve is slightly off, flow separation occurs. As water accelerates, it detaches, creating a localized vacuum of negative pressure. This triggers cavitation. Water boils at ambient temperatures, forming microbubbles that violently implode against the solid surface. The precise geometry of the OG shape neutralizes this threat. It forces the rushing water to stay firmly attached to the concrete, regardless of velocity. Mastering flow separation and preventing cavitation is what prevents the water from tearing the megastructure apart from the inside out. The water has survived the drop without damaging the dam's face, but now it is rocketing towards the fragile riverbed at supercritical, destructive speeds. To catch this runoff safely, engineers construct a stilling basin located at the very bottom of the spillway chute. Here, they trigger a hydraulic jump. Fast-moving, shallow water is forced into a deeper, slow-moving pool. This collision creates extreme turbulence, acting as a liquid brake to bleed off the kinetic energy within a confined area. The OG Spillway's job isn't complete until the deadly energy of the flood is neutralized and returned to a natural, harmless river velocity. Millions of liters gliding over the crest, racing safely down the chute, and crashing harmlessly below. This orchestrated operation avoids the catastrophic erosion and structural failure that would occur if the water were left unchecked. These images shift the perspective on these massive barriers. A dam equipped with an OG spillway functions as a dynamic hydraulic machine, designed specifically to process and survive extreme kinetic energy. Attempting to fight millions of tons of floodwater with stubborn brute strength results in failure. The OG spillway works through total submission to natural fluid dynamics. Engineers provide the exact geometric path it naturally follows in a freefall. The spillway takes an unstoppable force of nature and provides it as safe, frictionless exit. The most resilient engineering solutions are achieved by understanding and yielding to the laws of physics rather than attempting to defy them.